Good afternoon, everyone. So, thanks for being here today.
Good afternoon.
So, first, I would like to say thanks to all of you for registering yourself in the webinar series on the DC characteristics of the gallium nitride based heterostructure physical transistor using the Synopsys Sentaurus TCAD software. So, we will explore how Synopsys Sentaurus TCAD help us to explore the gallium nitride wide bandgap semiconductor that is used in the advanced power electronics application. So we will go with the presentation first, and then we will have a live demonstration of the software, and then I will also give you the time. So in that time, you can have a Q&A session. So without any further delay, let me start the presentation first. So this slide introduces the broader Synopsys simulation ecosystem. So at the top, we have the Synopsys Quantum ATK. That is basically atomic scale modeling software that enable the realistic material simulation by integrating the multiple simulation methods. So this quantum key is added for exploring quantum mechanical properties, electronic structure, and material and device behavior at the atomic scale. So alongside the Synopsys quantum ATK, we have the Synopsys Sentaurus TCAD, that is a next generation device simulator for designing and optimizing the semiconductor devices. So it supports a wide range of materials and device physics that make it suitable for both current and future technology. Synopsys also offer a full VSI package. So for that, we have the digital front-end and back-end tools for the RTL2 verification and physical implementation to the sign-up. And we also offer a full custom solution for the analog mixed signal and library design. So today we have this session on the Synopsys Sentaurus. So we will focus on this tool only. So let me give you the brief overview of the Synopsys Sentaurus ticket. So this Sentaurus TCAD is a clear industry-leading suite for the technology computer-aided design tools that enable the simulation of both fabrication process and device physics. So it supports both process simulation and modeling steps, or like deposition, etching, implantation, photolithography, and device simulation, which analyze the electrical behavior under various conditions. So the goal of this Synopsys Sentaurus TCAD is to bridge the gap between the physical manufacturing and the electrical performance that help us to optimize the device design before the fabrication. So this Synopsys Sentaurus TCAD provides the detailed insight into how materials and structure we have that help us to reduce the development time and cost. And here you can see we have exported the raw data from the device simulator. So we have the drain current versus drain voltage, and we have the spatial distribution of the electric field and the doping concentration. So these visualizations are very essential for validating the result design assumption. So this Synopsys Sentaurus TCAD is widely used across academia industry for its accuracy, flexibility, and integration with the other Synopsys tools. So here you can see we will explore the full width of this Synopsys TCAD product family, and this suite is modular that covering every aspect of the semiconductor simulation. So starting at the atomic scale, we have the Synopsys Quantum ATK that help us to simulate the materials and devices at the atomic scale with the help of quantum mechanical precision. So for the Synopsys Sentaurus TCAD, we have the process simulation. So in the process simulation, we have the Sentaurus process and Sentaurus topography that model the fabrication steps like etching, deposition, oxidation. And here we have the Sentaurus process explorer that will provide the emulation and the analysis tool. So the structure editing that is handled by the Sentaurus structure editor that help us to create our structure from scratch in 2D and 3D. And we can also define the geometry and the doping profile. So the device interconnect and simulation that is powered by the Sentaurus device, Sentaurus interconnect and the Rafael FX is model the electrical behavior and the parasitic effect. So it also comes with the GUI where we have the Sentaurus workbench that is basically a central framework that tie all the tools in a single unified environment. So we can tie the process simulator, structure editing device, and also the interconnection design. So the ticket to spice environment include guarantee, mystic, and random spice. So these tools extract the a compact model for the circuit simulation. So this integrated flow ensures the seamless transition from the physical modeling to the circuit level analysis. And this product family is production proven and support a 3D simulation that is making it ideal for the advanced node and the novel device architecture. Now, if we talk about the key modules that comes under the Synopsys Sentaurus ticket, so there are four modules are the Synopsys Sentaurus Process, Sentaurus Device, Sentaurus Visual, and Sentaurus Interconnect and Explorer. So the yes process that is basically help to simulate the device structure by using the fabrication steps like deposition, etching, and implantation. And the yes device that is basically help to simulate the electrical, optical, and thermal behavior of the semiconductor devices. So we have the Sentaurus visual, that is yes visual, that is basically a visualization tools that help us to interpret the simulation result through 1D, 2D, and 3D plots. So here you can see we have the Sentaurus Interconnect and Explorer that support the parasitic extraction and the layout analysis. So this workflow typically follow 4 steps: structure creation, Sentaurus process, Sentaurus device, and then Sentaurus visual. So this modular approach allow us to focus on the specific aspect of the device design while maintaining the integration across the entire flow. So whether you are working on the FinFET, SFET, CMOS image sensor, so this module provide the flexibility and depth that is needed to simulate the complex semiconductor behavior. Now, if we talk about the process simulation, so the process simulation is basically a foundation capability in the Sentaurus TCAD that enable us to model the semiconductor fabrication steps in 2D and 3D. So this slide highlights the core feature of this process simulator that comes with the 3D geometric modeling engine for the deposition, etching, and patterning. So it also comes with the adaptive meshing that ensure the simulation grid adjusts dynamically to change in the geometry and the species concentration that will improve the accuracy. We can also define the custom models by the API for the tailored simulation, and it comes with the various physical models like the analytic and Monte Carlo implantation, diffusion like a laser and flash sending, kinetic Monte Carlo or like mechanical stress, and also the oxidation and silicization. So this capability allow us to simulate the real world fabrication condition with the high fidelity. So here you can see we have exported the raw data from the process simulation. So we have the mechanical stress, kinetic Monte Carlo, adaptive meshing, and the oxidation. So these visualization are very essential, and that show how we can capture the complex physical phenomena. So by simulating the fabrication process, we can predict how design choice affect the device performance that help you to reduce the trial and error in the manufacturing. Now, if we talk about the Synopsys Sentaurus structure, so the Sentaurus structure editor is a very powerful tool for creating and manipulating the device geometry in both 2D and 3D. So it provides a graphical user interface and scripting capability for the advanced user. And we can also perform the geometrical operation. We can define the doping profile analytically, and it provides the direct interface with the meshing engine. So this flexibility allows for the precious control over the device architecture, which is very critical for the accurate simulation result. So this editor support various complex structure. We can go with the DRAM, a CIS image pixels with the micro lenses through silicon wire structure, and here you can see this is the GUI of this structure editor. So this editor will help you to create our structure in 2D and 3D view. So we can go with the various complex structure by the structure editor. So the structure editor is basically based on the geometrical approaching. So layer by layer structure we can easily create. But the process simulation will always provide the higher amount of accuracy as compared to the structure editor. Now, if we talk about the Sentaurus mesh, so Sentaurus mesh is basically a dedicated meshing engine within the TCAD tool that is designed to generate the high quality 2D and 3D mesh for the semiconductor simulation. So it supports both axis aligned and boundary confining mesh creation using the triangle and the tetrahedral. It also supports the tensor product meshing for the structure grid using the rectangle and the cuboid shape. So this flexibility ensures compatibility with the other, various simulation solvers, including box, discretization, and also the finite difference time domain method. So this Sentaurus mesh integrates seamlessly with the other modules like the device, process, interconnect, and EM-based solver that provide a unified simulation workflow. And the mesh quality that directly impact the simulation accuracy and convergence that is making this module very critical for the reliable results. So here you can see we have defined the meshing in the semiconductor devices, and here you can see this is the GUI. So this GUI will help you to enable the meshing for any particular layer of material, we can also go with the scalar and vector quantity, where we can define the meshing. Now, if we talk about the Sentaurus device, so the Sentaurus device is basically a core module for the analyzing the electrical, optical, and thermal behavior of the semiconductor devices. So it supports both multi-dimensional simulation in 2D and 3D, and it also accommodates a wide range of materials like silicon, germanium, silicon carbide, and today we are basically focusing on the third and fifth compound. So where we will use the gallium nitride based device structure. So it also comes with the various transport models like drip diffusion, hydrodynamics, thermodynamics, and Monte Carlo transport simulation that will allow us to choose the level of physical details that is appropriate for their application. And it also comes with the advanced physical models like the stress dependent mobility enhancement, quantization, random effect, doping effect, circuit mix mode, small signal analysis, harmonic balance, variability analysis, and many more. So these features make it a very ideal for simulating the modern devices such as FinFET, NAND flash, CMOS image sensor, UMOS devices. So this Synopsys Sentaurus device is particularly powerful for exploring variability, reliability, and the transient behavior that is making it indispensable for both research and the production environment. Now, if we talk about the Sentaurus workbench, so the workbench is basically a central framework that ties together all the TCAD module into a unified simulation environment. So it offers a project management tool, design of experiments, and optimization workflow, and job framing for the parallel execution. So this workbench allows us to define the scenario where we can set up the parameter, we can run the simulation across multiple nodes that will help to improve the accuracy and the scalability. So the integrated ticket data visualizer help us to interpret the result with the interactive plots and overlay. And this interface support the editable runtime modes that is making it easy to tweak with the simulation and the rerun the experiment. Now, if we talk about the Yes Visual, so Yes Visual is basically a visualization modules within the Sentaurus ticket that are designed to help us to interpret the simulation result through interactive graphical user interface. So it supports both 1D, 2D, and 3D plots for the devices and also for the output result. So we can rotate our models around any axis XYZ. We can zoom in, zoom out, and we can also reposition for the better view. And one of the key features of this Sentaurus visual is the ability to selectively hide the material or the region, which is help us to isolate the specific layer of the component for the focused inspection. Now let me give you some basic overview of this gallium nitride heterostructure field effect transistor. So the gallium nitride heterostructure field effect transistor are advanced semiconductor transistor that is built using gallium nitride based heterostructure material. So these devices are widely used in the high power and high frequency electronics application because of their superior electrical properties compared to the traditional silicon devices. So a gallium nitride or heterostructure field effect transistor typically consists of the aluminum gallium nitride and gallium nitride layer grown on their substrate. So similar to the other field effect transistor, this gallium nitride heterostructure field effect transistor also has a three terminal source, drain, and gate that basically help you to control the flow of current between the source and drain. So here you can see I have listed some of the advantages of this gallium nitride as well devices. So if you talk about the high electron mobility and velocity, so the structure formed between the aluminum gallium nitride and the gallium nitride layer that is basically enable the electrons to move very quickly, which improve the device electrical performance. Now if we talk about for the high power density, so gallium nitride SOH that can operate at a higher voltage and power levels that making them suitable for the power electronics application. Now, if we talk about the high frequency operation, so due to their fast electron transport and wide band gap of gallium nitride, So these devices perform well in the radio frequency and the microwave frequency range. And the aluminum gallium nitride material layer, and this is the aluminum gallium nitride that is basically a barrier layer that play a very crucial role in the forming a conductive channel at the interface with the gallium nitride layer. So the presence of source, drain and gate contact that allow the precise control of the current flow between the source and drain. So because of this advantage, gallium nitride heterostructure purified transistor are widely used in the RF amplifier, microwave system, radar system, satellite communication, and also the power electronics. So this is the device that we are going to create by using the structure editor. So let me give you some brief idea about all the layer by layer. So first we will create a substrate. So at the bottom of the device, that is basically we will create a substrate. So we provide the mechanical support for the entire structure. So there are various common material that we can consider for the substrate. We can go with the silicon, we can go with the silicon carbide, and we can also go with the sapphire. So like aluminum oxide. We can also go with the buffer layer above the substrate. So this layer will help you to reduce the lattice mismatch and the defect between the substrate and the gallium nitride layer. It also improves the device reliability and the electrical isolation. So if you see in the previous slides, then it will be more clear. Here you can see. So then we will have a gallium nitride channel layer that is basically act as a main channel material where the electron transport occurs. So the gallium nitride is basically a wide band gap semiconductor. This allow the device to operate at the higher voltage and at the higher temperature. So after that, we will create our aluminum gallium nitride barrier layer on top of the gallium nitride. So this barrier layer is basically help you to create a heterojunction with the gallium nitride layer. This is very essential for the device operation. And then it will form the two-dimensional electron gas. So it will generate at the top of the aluminum gallium nitride with the gallium nitride channel layer. And then we will enhance these properties. So first we will go with the gate to bias ramping where we can plot the IDVD characteristics, and then we will go with the state capture where we can play with the voltage, gate biasing voltage, and then we will sweep the drain voltage. So this part we will cover in the demonstration, and here you can see. Then finally we will plot the DC output characteristics of the gallium nitride heterostructure field effect transistor. Now here you can see these are the wide range of application where you can utilize this Synopsys Sentaurus TCAD. So whether you are working on the advanced logic devices, memory, power electronics, analog and RF, or optoelectronics. So this Sentaurus TCAD provides a tailored simulation solution. So if you are working on the logic devices, so it support planar CMOS, FinFET, nano FET, tunnel FET, and even digital devices. So in the memory, it supports NAND and NOR flash, DRAM, 3D NAND, VRAM, stream transfer of RAM, and in the power application, it supports silicon IGBT, super junction LDMOS, VCD, silicon carbide, and gallium nitride. So we are focusing on this gallium nitride power application. You can also utilize this Synopsys Sentaurus TCAD in the analog and RF application, or like silicon germanium SVT, HEMT, SVT, and it is also useful for the optoelectronics application where you can go with the CIS, image pixel, charge coupled devices, photo detector, silicon solar cell, and third and field solar cell devices. So thank you for listening to this presentation. Now I would like to switch on the demonstration part. And in the demonstration, I will show how we are going to create any kind of structure by using the structure editor, and then we will integrate that structure editor with the device simulator, and then yes visual. So let me open the tool. So here you can see I have already taken the access. So let me execute. So I am going to open the Sentaurus workbench. That is basically a unified environment that integrate all the tool into a single GUI. Now we are going to open it. So let me click on the OK. So you can see this is the graphical user interface of this Synopsys Sentaurus TCAD, that is called Sentaurus workbench. And here you can see we are going to select the tool one by one. So first we will select the structure editor, then we will select the device simulator, and then we will select the yes wizard. So I am going to create a new project. So here you can select the project option, and then you can click on this new, and then you can go with the hierarchical project. Now here you can see we have the option to add the tool. Now you can select right click and go to the add option. So you can see this is the main advantage of this Synopsys Sentaurus TCAD software. So it combines all the tools into a single graphical user interface. So we can go with yes process. So if you are going to define the, if you are going to create a structure by using the fabrication steps, then you can use the yes process. And if you want to create any kind of structure by using the geometrical approaching method, then you can go with the ESG. And then we will move to the yes device for the electrical, optical, and thermal analysis. So I would like to select this ESD. You can select this, okay. Now here you can see we have the ESD. So I would like to click on the okay. Now you can see the ESD has been added. Now I would like to select it, right click and click on this add option to add up the ES device. So here you can see it will provide the direct integration with the ESD and with the ES device. So let me select the ES device after the ESD. Now we are going to create our structure by using the Sentaurus structure editor, and here you can see we have the option to define the command. So if you know the script, then you can go with the edit input and you can write the command. And if you are not aware about the scripting engine, then you can open the GUI. So let me open the GUI for this structure editor. So you can see this is the command for the opening the structure editor. So this is the structure editor that is mostly based on the geometrical approaching method. So we are layer by layer structure we are going to create, and we can also define our exact device dimension. So here you can see we have the view, and in the view you can see we have the GUI mode. So if you are working on the two dimensional devices, then you can go with the 2D mode, and if you are working on the 3D devices, then you can select the 3D mode. So I am going to select 2D mode because I am going to create a 2D device. And then here you can see we have the list of material database. So whatever the material that you want to select, you need to click, and then you can go with the shape. So in this shape, you will select the rectangle. So first, I would like to select the silicon nitride that is actually for the passivation. But we can also go with the substrate first. So let me create a substrate. So for the substrate, I would like to choose the material silicon carbide. So here you can see this is the silicon carbide material. And in the draw, you can see we have the option to define the outer region naming, and you can also go with the exact coordinate point. So if you know the dimension of your structure, then you can go with the you need to disable this auto region naming, and you can click on this exact coordinate, and then you can define the shape of the structure. So I am going to select this rectangle shape. You can see the rectangle shape has been selected. Now I would like to create here. So here you can see we are going to define the vertex in the x direction and y direction. So for the silicon carbide, I would like to define the direction. In the x direction, I would like to take 2.073. This is the unit in the micrometer. And here we are going to define in the y, I would like to go with the 02 5.80. And then in the x2, I would like to take 2.083. So you can see I am creating a 10 nanometer silicon carbide substrate. So then click on this OK, and here you can define the region name. So this is our substrate. So I would like to define here. So this is the SiC substrate, and then click on this OK. So here we are going to, you can see. So this is the substrate region. Now I would like to select the silicon nitride for the passivation. So let me select the, yeah. So this is the silicon nitride. And for that, I would like to define their coordinate point. So here I would like to take 0.0, and in the y also 0 to 5.80. And here I would like to take 0.050, around 50 nanometer, and then click on this OK. Here you can see this is the region name second. So here I would like to define passivation, and then click on this OK. You can see this is the silicon nitride passivation layer. Now I am going to define the gallium nitride cap layer. So for that I would like to select the gallium nitride material here. You can see we have the list of material that you can select. So this is the gallium nitride that has been selected. Now I would like to define the exact coordinate point. So here I would like to take 0.050 to 0.053, around 3 nanometers. And in the y direction, I would like to take 0 to 5.801. And then click on this OK. So this is the cap layer. So here I would like to define gallium nitride and the cap. So this way we can easily design our structure. So you can see it is overlapping here. Now we are going to create aluminum gallium nitride barrier layer. So let me select the material first. So this is the aluminum gallium nitride. Now you can see the material has been selected. Now we are going to define the exact coordinate point. So for this aluminum gallium nitride barrier layer, I am going to create a 20 nanometer thickness with the thickness. So I would like to take 0.053 to 0.073. So it is around 20 nanometer. And here I would like to take 0 to 5.80.
Hello.
And then click on this OK. Yeah,
Hello.
please.
Sir, sorry for the interruption. Sir, can you please share the dimension of that silicon carbide substrate?
Yes, sure, I will share. So for this silicon carbide substrate, I have taken from 2.073 to 2.073. It is
Okay, sir.
around 10 nanometer.
Okay, sir.
And in the y direction, I have taken 0 to 5.80.
Okay, sir. Okay.
Now you can see this is the barrier layer that I am going to define, and then select this OK.
Sir, then
So
second part is,
yes, please.
sir, for second vertex, what is the coordinate of x and y for silicon carbide substrate?
So the x direction I have taken from 2.073 to 2.083, and in the y I have taken 0 to 5.80.
Okay, okay, sir. Thank you, sir.
Yeah, okay. So you can see I have also taken the aluminum gallium nitride, that is basically a barrier layer, and I have created 20 nanometer with the thickness. Now I am going to create aluminum gallium nitride spacer region around 2 nanometer at the bottom of the barrier. So let me drag, and here let me define the coordinate point. So 0.071 to 0.073, it is around 2 nanometer. And in the y direction, I would like to select from 0.0 to 5.80, and then select this OK. Here you can see we are going to define the region name. So this is the spacer region, and then select this OK. So it has overlay. Now after creating this spacer region, now I am going to create a channel region. So for that I would like to select the gallium nitride material. So let me select the gallium nitride. You can see the gallium nitride material has been selected. Now let me define the coordinate point. So for that, I would like to go with the 0.073 to 0.078, around 5 nanometer. And here I would like to take from 0 to 5.80. So this is the thickness of the gallium nitride channel. Sorry, 5.80. And then click on this OK. Here you can see we are going to define the region name, and this is our channel. So let me define the material and the channel. and then click on this OK. Just do this. Now we are going to define the gallium nitride buffer. So gallium nitride is already selected. Now let me define the exact coordinate point. So I am going to create a buffer region around 1.995 micrometers. So let me define the coordinate points from 0 to 78, and here I would like to take 2.073. So this is the direction X, and in the Y I would like to take 0 to 5.80. So this is for the buffer region, and then you can select this OK and define the buffer. So this is the gallium nitride buffer. And once you define, you can select this OK. Here you can see we have created a complete device. Not the complete one, but we have defined all the layers. So once you defined, now we are going to add the gate, source and drain. So for the gate, source and drain, here you can see we have the option to select the edge. So you can see we can select the vertex, we can select the edge, we can select the face, we can select the body. So I would like to select the vertex, and here you can see I would like to click on this view option, and in the view here you can see we are going to, sorry, let me select the edit, to edit and add vertex. So here you can see. Now I am going to define the vertex. So for the source I would like to take 0.05 to 0.0. So this is the first vertex for the source. Here you can see it will going to create. And now I'm going to create a second vertex. So for that I would like to take 0.050 to 0.50, and then click on this OK. Here you can see this is the second vertex. So this is our source. Now we are going to create a drain here, and then we will create a gate. So for the source I would like to take the vertex
So can you show
0.
how can we take the vertex for this? Okay.
First we have to define the coordinate point for the vertex, and once you define, then you can go with the source, drain and gate contact. So we will set. So here you can see I am going to define 5.3 for the drain, and click on this OK. Here you can see this is the first vertex. Now I am going to define the second vertex for the drain, and that is around 0.05 to 5.8, and then select this OK. Here you can see we have the second one. Now we are going to define the gate. So again I'm going to create a vertex, and first vertex I would like to take from 0 to 1.0 to 1.5. This is the first vertex. Select this OK. Now you can see this is the first one, and now I'm going to create a second vertex, and that is around 0.0 to 2.3, and then select this OK. Now you can see. So once you define the vertex, you can go with the contact, and you need to click on the contact set, and here you can see we need to select the define the contact name and then their color. So this is the RGB. So first I would like to define the source, and I would like to keep this red color, then click on this set. You can see source has been added. Now I am going to define the drain, and this is also red color, then click on this set, and now I am going to define the gate, and let me change the color. So I would like to take a 0 and 1 here. So this is the green color, and click on this set. So once you define the contact name and so their color, you can click on this close. Now we are going to add here. First you can select this arrow, and then you can go with the source. As you can see we need to select the source. Let me zoom it. Let us see. This is the source that we are going to select. Sorry, here we have selected what is. So we have to select is like this. So you can see this complete one has been selected. Yeah. Now you can see this highlighted one represent the source. So we are going to click on this contact and set contact. It will show the red color. You can see. Now we are going to select the gate. Gate has been selected, and here we can select this region and then click on this set contact. So we have set the source. We have also set the gate. Now we are going to set the drain. You can see this is the drain. Let me zoom. Yeah. So this is the drain, and click on this. Here we have to select the drain, and then click on this set contact. So you can see we have defined the complete device. So where we have created substrate, we have created gallium nitride cap region. We have also created aluminum gallium nitride barrier. We have created aluminum gallium nitride spacer region. We have created gallium nitride channel region. We have also created gallium nitride buffer region. And we have taken silicon nitride as a passivation around 50 nanometer. So once you define the structure, we can go with the doping profile. You can go with the device. You can go with the constant profile placement. You can go with the analytical profile placement. You can see. And then we can select the region that we have selected. And here we can select the analytical doping profile. And then we can select all the parameters. So their peak concentration, their junction, their parameter, lateral direction diffusion. So this parameter we can select. And if I select this first one, constant profile placement, you can see we can define the doping here. And once you define the doping, so I'm not going to define the doping here and the mesh because I have already generated a script for this gallium nitride. But we can also do that. And here you can see this is the mesh. So you can define the mesh. Let me go with the refinement placement. You can select the particular layer material and you can define the mesh size, the element size, and the minimum and maximum element size for the x direction, y direction, because it is a two-dimensional device. If you are going to create a three-dimensional device, then you can go with the z direction as well. So once you've done, you can copy this script, and this script you can paste in the workbench. Here you can see, you can go here, select this edit input, click on this command, and here you can save. And once you save, you can go with the device simulator, and in the device we have sorry. So we are going to simulate gallium nitride test bed. So if you know the script, then you can go with the command. If you are not aware about the scripting engine, then you can go with the yes device wizard. In the yes device wizard, you can see we have the option to select our specific application. So we have selected a wide bandgap device. So I would like to go with the third N device. Click on the next. Here you can see we are going to select this aluminum gallium nitride and gallium nitride heterostructure field effect transistor on the oxide substrate. You can also go with the gate injection transistor. You can go with the pin diode. So based on your device structure, you can select the supported device here and then click on the next. Now you can see here we are going to select the task. If you want to define the drip diffusion, then you can enable this IDVDS with the drip diffusion and the self heating. And if you want to define the hydrodynamic, then you can select the second one. So I would like to go with the first one, IDVDS with the drip diffusion. And here you can see we can customize the physical models. Like we can define the ambient temperature, we can define the area factor, we can define the transport models, and we can enable and disable any model as per our need. So you can go with the carrier Fermi statics, you can go with the band gap narrowing method, harmonic emission, piezoelectric polarization. So actually in the like piezoelectric we have the different options. We have the stain model and we also have the stress model. So that will help you to compose the polarization effect in the gallium nitride device. So you can also edit the script as well. So once you define all the parameters, then you can go with the physics at the interface, where we have created the interface between the aluminum gallium nitride and the nitride. So you can define the interface trap density, you can define the interface trap type like the donor, acceptor, So once you define all this parameter, you can go with the next, and here we can define the numerical settings. Like we can define the solution extrapolation, we can enable it, we can off, we can define the parallel option for the multiprocessing system. So and then you can set the upload, then you can click on the next. So here you can see this is the script based on the selected parameter. So once you click on the finish, then it will generate a script in the S device. So you can see this is the script that has been generated. And this script is editable. So before simulation, if you want to modify any parameter, if you want to add up more analysis part, then you can write it and you can save. So once you do that, you can close it and then you can go with the, here you can see it automatically define the IDVDS because we have selected IDVDS with the derivative diffusion settings. So this way we can easily create any kind of project from scratch. So we can go with the structure editor, then we can go with the S device, then we can go with the ES visual. And if you're exporting that in the script for the like fabrication step, then fabrication steps, then you can go with the processing design. So let me show the data. You can say I have already simulated in the heterostructure. So here you can see, this is the estate gallium nitride AC characteristics. So here I have shown like how we are going to create any kind of ES device. So here I have added multiple ES device. So we have ran, we have defined the voltage, gate voltage, and then we have also sweep the drain voltage. So you can see this is the device structure. Now this simulation is already completed. So let me show the output file. Here you can see this is the ES visual that is roughly help you to interpret your data in 1D, 2D and 3D. Now we can also show the information about the node. So let me show. So here you can see, you can click on this I tab. So this is the node 2 and this is the EST. Similarly, we can go with this node and here you can see, this is the node 4. So this way we can also find out the node information. So once we're done, you can go with the ES visual and here we are going to load the file. So let me select the location. So I think my project is under, here this is the one. This is the application library and here you can see this is the hetero. So here we have the SVET gallium nitride device. So you can see we have already simulated. So we have the TDR file.tlt file. So TDR file will basically help you to show the device. And if you want to upload their like IDVD, IDVG, characteristics, then you can go with their .plt file. So let me show the TDR file. You can see this is the M3 band. And click on this OK. So here you can see we have the aluminum gallium nitride. Here you can see this. So this is the advantage of this ES visual where we can hide the layer. You can see this layer has been hide. We can define the meshing here. We can enable the meshing. There you can see. We can also mesh in the X and Y direction as well. So let me open the complete device. So let me show the node information first. I think we have to select this one. This is the node 4, node 3. So let me open the S visual. I'm going to load. So here at the node 5, 6, and 7, you can see this is the 4. So this 5, 6, 7, and 8. Here we have added for the IDVD and 10 and 11 we have simulated for the IDVGS characteristics and this one is for the IDVG RAM. So I'm going to open this IDVD. Let me. This is the node 10. Sorry, node 5. So this is the node 5 here you can see. This is the TDR file. Let me open the final device. Here you can see. So let me, yeah. So here you can see we have the routing concentration. We can also go with the band gap. You can see. We can go with the conduction band energy. So here we have the scalar plot, we have the vector plot, and we have the interface plot. So we can see we can go with the net trap charge, we can go with the trap occupation, and the vector we can go with the electric field, you can see, and we can also go with the polarization, and this is the scalar plot. So we can go with the electrostatic potential, you can see. So this way we can plot the output. And let me plot the ID BD characteristics. So for that I would like to open the PLT file .plt. So first I would like to select the node 5. This is the node 5. Yeah, this is the PLT file. You can open it. Here you can see we have the data, we have the source, gate and drain. And once you select this, let me select the our drain. You can see this is the drain has, yeah, you can see drain has been selected. Now I would like to select the inner voltage. And this inner voltage I would like to draw at the x-axis. And after drawing this, I would like to draw the drain current at the y-axis. This is the total current and plot at y-axis, you can see. So this is the IDVD characteristics for the node 5. Similarly, we can also take the node 6 here. Let me import. This is the node 6. Let me open it. And just we have to select the node 6 here and select the drain and go to the total current and you can plot to the y-axis so that we can merge the graph as well. You can say this is for the node 5 and this is for the node 6. Similarly, we can plot for the node 7. Let me go for the 7. This is the PLT file. Select this open. This is the node 7. Select the drain, select the total current and click on the y-axis. Now you can see. So this is for the node 5, 6 and 7. So this way we can easily plot the data. Let me plot the complete IDVD characteristics. So for that I would like to select the node 8 as well. So this is the node 8 PLT file. Select this data, select the drain, select the total current as the y-axis, as you can see. So this is the complete data for the IDVD characteristics from node 5 to 8. Yeah. From here to now we are going to go with the IDVD characteristics. So let me close it. Let me open it again. Sorry. So this is the yes result. Let me open to the file. So let me open. The TCAD version. This is the application library. This is the Heterostructure. This is the gallium nitride device. Now for the IDVC, I would like to select the node 8, sorry, 10 and 11. This is the node 10, 25, select this open. And here we are going to select the gate and their voltage at the x-axis. This is the inner voltage at the x-axis and the drain and their total current at the y-axis. Now you can see.
Sir, what is the difference between inner voltage and outer voltage there?
Pardon?
Sir, what is the difference between inner voltage and outer voltage? It is showing there.
Yes, here it is showing the inner voltage and the outer voltage that we have in the PLT file.
Yes, sir. What is the difference?
Yeah. So we want to like difference between these two. Just
Yes, sir. Yes, sir.
let me show with the let me show with the structure. Sorry. Let me open their PLT file. Sorry, .tdr file. Then it will be more clear. This is the node 10. This is the TDR. And here we go. Yeah, so the basically the outer, let me go with the data. Yeah, you can see we have the inner voltage and the outer voltage. So this outer one regulate the output voltage difference, while the faster inner loop manages current. So the inner one will manage the faster current and the outer one will regulate the loop. For the slow looping, you can go with the outer voltage, and for the faster loop, you can go with the inner current, inner voltage and the inner current.
Thank you, sir.
So let me open the node 11. This is the PLT file. So let us open. Here you can see we have the node 11, and here we are going to select the trend, and their total current are the y-axis. You can see. Yeah, so we have shown how we are going to plot in kind of IDVD and their IDVD characteristics. So this way you can also go with their voltage ramp. So for that, let me import, let me close it, and let me open it again.
Okay, sir. Sir,
Yeah, please.
sir, can we get the results in tabular form? The graph which we have find. Can we get the result in tabular form?
I think we can export,
Like,
but I will, yeah, we can export that, but I will check and I will let you know how we can export that.
okay, sir.
Yeah, the export option is available, so we can export the data as well. This is the application library, this is the heterostructure, this is the gallium nitride, and let me select the node 4. Yeah, like similarly we have the time source, gate and trend. Yeah, so this is all what from my side. So we have the time limitation here. So if anybody has any question, they can let me know. This is my contact details. You can also
Hello.
take the screenshot of this. Yeah, please.
Sir, means you didn't mention about a machine. Means, for example, it's a large wide band gap materials. So the machine points is layer to layer. What should the machine? So what is the minimum machine and what can be the maximum machine can go? If any converge issue comes while the IDE and CV, because the lot of issue of a converge issue for lot of issues regarding to the GAN hand is only about an
Refreshing the matching
uh,
conversions.
hello.
Yeah, please. So actually, mesh
Means lot
conversions
of
like a
uh, lot of
so
issues
we
are there.
cannot
No.
like tell you the exact. We cannot tell you the exact like a missing point that you can define for any kind of devices. So you can do trial and error method. So you can define the final mesh, and then you can go with the convergence. So if you're facing again the problem, you can define again the final mesh, and then you can go with the
Okay.
simulation.
Okay. If
So
the
telling the
converge issue
exact.
is not
Okay,
regarding to
I,
the, if for example, if the converge
Yes.
issue is not regarding to the S device, sorry, SDE, means we have to make some parameters regarding to the S device in S device now. For example, some
Yes.
physics is there, some error means RH electrons is there, RH holes are there. So means what are the parameters is required to vary. For example, means SDE we can vary the mesh points. But coming to the same thing, what can we vary in the S device apart
No,
from the
in
step
mesh
size?
device. No, we have to define the like the missing point before the ES device. So whenever you are creating your structure, you can define the mesh, and once you are not getting any kind of convergence issue, then you can take this input file into the ES device. Then
Yes,
you will get
for
better result.
no,
But if you are doing
the
the meshing point in the ES device itself, then you have to tackle with the more like convergence issue. So you have to vary all the parameter like their doping profile, their mass density, their mass element, that we need to vary.
So
It
can
is it is a proper in the SDE, but it comes an a concern issue when we keep the in S device. It is already
I
there
will
in
su-
the
yeah,
Sentaurus.
I will suggest you can define the meshing before the SUIs. That will be like provide the better
That we are
accuracy.
doing, sir. That we are doing. I'm asking a question. If the SDE is fine, when we are adding to the Sentaurus workbench, and we are adding an S device. If you are synchronizing both, then the converge issue comes in an S device. So the mesh is okay, the mesh is fine in the SDE point of view. But coming to the S device point of view, if the converge issue
Workbench.
comes,
Okay.
workbench comes. So means what are the parameters? Because lot of converge issues are there in the GaN hem. So GaN is wideband GaN material. That's the reason I'm asking.
So I think there are various parameters that need to be considered, like the stress parameter, displacement, reaction force, and also or the like difference and sense between the refinement that we are defining in the yes mesh. So there are various parameters that we have to consider for the convergence issue.
so please can you show the solve section of this simulation that you did?
This one.
Solve section of this simulation that you did. The solve section. I want to see how did you vary from minus to plus VGS.
Okay. Okay, let me see. So you can see here we have vary. So this is for the voltage ramp. We have defined the node 2 and node 3, and here you can see voltage, and we have defined the initial step, minimum step, maximum step, and then we have defined the volt. So this is for the ramp one, and we can also go with the IDVD. Yeah, here you can see. Here we have defined voltage around 50.
So can we do it in a single file also by changing the variable for this?
Yes, you can also create a single file. So
So how
for
can
the
we do that?
better view, we have added multiple SUIs so that we can show the graph at particular point, at this particular voltage, at this voltage. But you
Sir,
can also combine.
how can we add the surface traps in these GaN devices at particular this
So you want to add up some surface.
traps? Because there are always the traps because of which our device performance is decreasing. So how can we introduce in that?
So actually, you have to go with the physics manual. But if you are not getting, let me show with the S device, ES result. If it is available, then we can easily create. If it is not available here, then we have to write the script in the command with the detail scripting. This is the aluminum gallium nitride.
So we can vary here the interface trap density.
Yes, yes, yes. Here we
But
can
sir, at
vary.
which interface it is wrapping? Because there are so many interfaces like for AlGaN or GaN layer and
No, we
for
have
substrate
selected
and
here. You can
layers.
see this is the aluminum gallium nitride and the nitride layer, gallium
So
nitride.
for
So this is
for
the
multiple,
interface
we can also
for
add
this one.
for us. No,
So
for
for the
this one
multiple
it's
one, you
fine.
have to write the script and the editor. Yes.
Okay, we
But
have
the
to write it.
interface, we can select a single one. So this way you can add up like SD here, where you can vary for the gallium nitride nitride, and then in the second ESD you can take another layer, another interface layer, and you can vary the trap density value. And if you want to combine all this into a single, then you have to like copy and paste. all the code into a single discrete text.
Sir, one more thing, like the example that you have demonstrated, you initially use vertices for defining the source, drain, and gate, right? But in
Right.
the run simulated here, I don't think it's vertices, or you define a complete rectangular image for this example for have to gain DC characterization. If I'm looking like this, it's I don't think so. It's body they are defining, or it's only the vertices for the describing the gate source and
No,
drain.
here actually they have defined the thickness of the aluminum gallium nitride, and they have defined the thickness of the, yeah. So they have defined two thickness for the barrier and the cap layer, and that value they have considering for all the like all the material layer. But when I have created, I consider this value by adding, like if you are going with the 0.20 that I have already added in the material layer. So I have
Sir,
created a complete divided structure
sir,
in the first one.
one more question. Like when we are fabricating the GaN for making the Schottky or ohmic contacts, we we use different types of layer like titanium, aluminum. There is a combination of layer. So can we do it in this also, or we define work function for upper material or lower? How on what basis they are defining the contacts here?
And that I need to check, then only I can confirm to you how we can define it.
So for that, in that case, we actually have the the contact code that you have. You define the resistance and the work function itself. In TCAD, you cannot do such kind of things. You just take those values and you define in the contact
But
signal.
for defining the work function, for which material we have to take the
Oh,
uppermost.
for that, since you are using titanium, it would make a titanium nitride itself. Then if you are
Yeah.
using aluminum again, then that would change the work function itself. So there are various papers which are defining what is the work function for the particular thickness of metal. So whatever you are using, there are experimental values available for that.
For that we need to do, because there we are using it for combination, like uppermost layer is a gold for insulating this, and lower are the titanium, AU, and the combination for these. Thank you, sir.
Yeah, so if anyone has any query, they can let me know. Or you can also take a screenshot of this contact details. You can write a mail, whatever the query you have, or you can also go contact directly with the given number. So if there is no query, I think we can conclude this.
Sir, hello,
Yes,
sir.
please.
Sir, can you have the recorded version of this
Yeah,
entire?
yes. After this session, we will provide a recording of this session
Oh,
to
okay,
all the
okay,
participants.
okay. Thank you, sir. Thank you, sir.
Yeah, okay, thank you.
Sir, what about the heating or self-heating of the device?
You can see we have the heating and self-heating parameter that you can enable, and you can go with their analysis. So I think I have already shown that. Let me load it. Go to the yes device, right click edit, yes device charge. And let me select the wide band gap. This is the third and let me maximize it. Click on the next. Oh, this is element. Next. Here you can see. We have the drift diffusion with the self-heating, and we have the hydrodynamics with the self-heating. So basically, the self-heating evaluate the temperature as in the component, like the primary semiconductor devices.
Okay, sir. So one more thing, like what about visual source modeling? Can we directly connect this to some circuit simulation?
Actually, I don't have idea about the circuit simulation. So I deal with the TCAD and the atomic systems. So I
Uh,
will check that one, how we can explore the data with the circuit simulator. So
okay.
you can write a mail to me or you can go with the directly contact with the number.
Okay, sir. Thank you, sir.
Yeah.
Sir, I want to ask, will there be more lectures like these?
Yes, definitely we can definitely organize different sessions for this Sentaurus TCAD and the quantum ADD as well. So we will share the information in the WhatsApp group.
Okay, sir. Thank you, sir.
Yeah. So if there is no query, yeah. So from my side, thank you so much to all of you for joining this session. So I hope you enjoy this session. So for any kind of support or technical support or any query, you can just let me know. I will try to help you. So once again, thank you so much.